Okay, perfect. So this is lecture 25, and we start with a summary of week 13. And that was devoted to semi-flexible polymers. First of all, the Kratky-Porod Model, which is kind of a geometric model where the bead rods have finite length B, as usual, but they also have a fixed angle theta, fixed bending angle, and we're only taking the statistical average over the okay, so far on rotation, the rotation angle phi. Statistical average over phi in 0 to 2 pi uniform. So here, from purely geometric consideration, we get the tangent-tangent correlation to be minus cos theta to the power of n. And also, so basically, as soon as we can get the tangent-tangent correlation, we have the end-to-end distance vector and entire moments and the radius of gyration. These are all within reach and computed. But this is more or less where it also stops. But here, what is useful as an insight from the Kratky-Porod model was that it's the first model where we consider that the polymer is locally almost straight, as there is a bending energy cost, which is proportional to the product of subsequent tangents. So it's proportional to cos theta. And now when taking the continuum limit, we assume theta to be of order pi, send b to 0, n to infinity, and keep now the length of the entire polymer fixed, taking the rigid rod as a reference state compared to the Gaussian chain. And this defines the persistence length, which is the intrinsic length scale of semi-flexible polymers. And in this framework now, the tangent-tangent correlation can be written as an exponentially decaying correlation with characteristic length scale is given by the persistence length. And similarly, the end-to-end distance is given by, this is the full expression that we can solve for, which has two limiting cases. One we've seen before, namely for a very flexible, semi-flexible polymer. This is the Gaussian chain limit. And L squared for a very stiff polymer that is a rigid rod. And so what we see as well with like taking this limit, if we look at identifying the end-to-end distance scaling, we can identify the Kuhn statistical segment. B is R squared over L to LP. So that means that if at the scale of 2 persistence lengths, my semi-flexible polymer behaves as if all angles are equally probable. So then it sort of loses its orientational correlation, which is obviously also obvious from the exponential decay of the subsequent tensions, right? Which in the Gaussian chain are not correlated. And so you see the correlations decayed to significant order at twice the persistence length distance. Another more common description of semi-flexible polymers is the Wormlike chain model, where we write the bending energy as minus J summing over subsequent bonds, and the angle enclosed by subsequent tangents. Again, this should remind us of what we solved for in as a tension-tension correlation and the paramagnet. Similar, we can take the continuum limit, again, B to 0 and to infinity, L and B, and here also the interaction per site fixed. And that allows us to define kappa as epsilon L or LP KB T, the bending stiffness. And then in this notation, the Hamiltonian becomes which is what you would derive from an elastic rod, or this would be in the tangent formulation, this would be what you get from the Hamiltonian above. No difference here is that we assume this tangent always to be 1, so which is the local inextensibility. And this also follows from rotational and translational invariance. And now to learn about the statistics of the system, we can, similar to the Gaussian chain, we can map it to a diffusion equation, where now the propagator where now we here consider diffusion on a unit sphere, with D being KBT over 2 kappa, the bending stiffness. And then the Green's function solving this diffusion equation being given by the path integral over all conformations of this semi-flexible chain. Oops. And minus 2 kb t 0 this. And so the challenge here is that there's this constraint that we have to consider, this inextensibility, which makes it hard. And the way out was to look into the weakly bending rod approximation, where we now consider that if I actually trace out my semi-flexible polymer, then to good approximation, it's extended anyway, so I can, at a specific point along the contour S, I can distinguish dynamics as the undulations relative to the rigid rod, and the stored length, which is stored length in the undulations. And now it was here instructive to see that if we now consider parameterizing the curve in terms of these coordinates, we see by looking at the tangent, which is defined as the derivatives, and considering that the tangent magnitude has to be equal to 1, which states that the which is 1 minus 2. Yeah. Square too early. Yeah. We see that this is higher order. These two cancel. And so we see that the stored length is in higher order to the undulations, which allows us to simplify the Hamiltonian. So this we can see as higher order to our perpendicular. And so that makes the weakly bending rod Hamiltonian much simpler because now we're only integrating over the undulations. And that was very useful because we know that these transverse fluctuations due to the equipartition theorem, we know how much energy goes into them, so we can calculate the transverse modes based on equipartition theorem, and then, for example, find the force extension relation that is physically insightful, because here we see that summing here over the modes of an extended polymer, we get again two limits. One for small forces, where we here have a term of like the length being reduced to thermal contractions, and then being extended by the force acting subsequently for small forces. And small here determined by, as a reference value, the force of Euler buckling. So that's Euler buckling force. And at large forces, we find that the force extension curve diverges as expected. So that was on the statistical equilibrium physics of polymers, and as I advertised, like the challenge in nowadays physics is to describe non-equilibrium. So we still seeking to find principles of how we can describe non-equilibrium systems. And so to give you a small glimpse of what kind of methods are out there, I'm going to devote today's class to the topics of polymer dynamics. And so I'm going to use tools that will be introduced in a formal way in stochastic processes, which would be happening in the summer. So, which, you know, what I like about, so stochastic process is basically how to describe random processes. and their dynamics. And it's an amazingly rich toolbox in the sense that you can use it to describe very diverse processes. And so that's why I feel that it's really a very good basis to have, because of this, you know, if you're interested in non-equilibrium processes, it's very rich, because there's a lot of things that you can still, I mean, look, we mapped here a lot of processes on diffusion on a unit sphere, you know, on the diffusion process. And in a similar fashion, there's a lot of processes that you can match on these stochastic processes framework. So now dealing with polymer dynamics, I will first go back to the Gaussian chain and develop methods in the Gaussian chain model, and then briefly give a lookout into how to describe semi-flexible polymers. So we describe now a polymer again as a Gaussian chain of n beads. Remember, they had a spring constant of 3 kBt over b squared. So we're back to the setting that, you know, spring bead model it is. And this is R0, R1, and this has a typical length b and goes until Rn. Now I want to describe the motion. And so the motion of each bead is given by Newton's law, right? So we have m dvi dt, which is our inertia term, is equal to the forces acting on the speed. And of those, we have a viscous force that is proportional to the velocity. And that's actually, I think it's experimental physics 1, right? This friction constant of the viscous force for a sphere can be calculated in its 6 pi eta, the viscosity of the fluid A, that's Stokes' law. So it's proportional to the radius of the bead, that's the important thing. And then we respect that these individual beads, they are connected to the neighbors by their springs. So they're two elastic restoring forces that I have to consider. One for the neighbor to the left and one for the neighbor to the right. So that's KRI minus RI minus 1. That's one spring. And then there's KRI minus RI plus 1. That's the other spring. And then I'm in a microscopic setting where I also consider that the thermal environment will give a random noise, which I describe here. That's a random noise with 0 mean, which means that at one point in time, this noise may push you to the right, on the other, another point to the left, and on average, there's no net push. Now, this is the full equation, which is driving the dynamics, and obviously, it will. We can already read off what is the time scale over which these dynamics of an individual bead will equilibrate, and so the time to equilibrate is given by, this is driving the time dynamics, so the time scale is given by gamma over m, right? This is the scale. So tau, which is, m over gamma, 1 over seconds, this is the time scale, is m over gamma. Now, I can estimate how these two properties scale, right? So the mass the mass of a bead obviously scales with its radius to the power of 3, that's volume, right? And we just noted Stokes' law that the friction of a bead scales linearly with the radius. So this scales totally with a squared. Now, given that we consider polymers, these are really, really tiny, so the radius of the individual beads is going to be really small. And so you can read off that the time scale to equilibrate is very short. So this is very short for small beads. And therefore, I can consider the dynamics of this beads to be in an equilibrated state, and neglect the inertia term. Consider only overdamped system. So that means that what we have here is actually now only considering the terms on the right-hand side and replacing the velocity as a time derivative of the position of our bead, an equation for the position in the bead position only, which is then minus k. Let me lump these terms together. We have a 2ri minus ri minus 1 minus ri plus 1, and this noise term. And also just a few words on the noise. So this random forces are characterized by so-called white noise, and white noise being defined by the average of this noise being 0, and the second moment, of I alpha denoting the Cartesian component, psi j beta t prime. This is 2 gamma kbt delta ij delta alpha beta delta t prime. And other definitions of the noise are possible, but this is the standard. Yes, I'm recording, right? Am I? Yeah. This is the standard definition for white noise, which is the one that you will encounter mostly. You may notice that this equation of motion is obviously only true for those beads in the middle of the polymer. We should specify additional equations for the two end ones that are only connected by one spring. So for the end beads, we accordingly find that the R0 dt is minus k R0 minus R1, psi 1, psi 0, sorry. And similarly, gamma drn dt is minus k rn rn minus 1 plus psi n. And now with these equations, we can look at the motion of the center of mass, which is a convenient shorthand because the center of mass is just the average of all positions of all beads, or 0. And so we can equivalently sum over all these terms. So that says then that the gamma dr center of mass dynamics dt is given. And so what we find here is now that all the springs, because they are oppositely symmetric in all neighbors. If I sum over all of them, all of these terms cancel out. And the dynamics of the center of mass is really just driven by the thermal noise. So that's then 1 over n. And that's very convenient because we know we have the noise specified, so we can actually from this learn about the correlations of the center of mass. Center of mass alpha at time t minus center of mass alpha at 0. So what's the average dynamics over time? Because it's the average of the noise is 0. This is 0, and only the second moment is more interesting, where we have then alpha t minus RCM alpha 0 times CM beta at time t minus R CM beta at 0, another bracket, and then this is 2 gamma kBT, sorry, there's an n gamma coming on, 2 kBT n gamma delta alpha beta t. So what we see is that over time, the center of mass diffuses with the diffusion constant as defined here. So that would be R squared dt. So that's the diffusion constant. So the looking at the center of mass is obviously useful, but we want to learn also about the dynamics of the polymer. So how is it wriggling in itself, not just moving as a whole? For that endeavor, it's useful to think about to map the system into normal modes. And normal modes means that we want to decompose, sorry about my equations. So in these equations, the position Ri depends on the neighbors, and I want to find a formulation that I can write the individual quantity of index I to only be depending on this quantity on I, like I want to diagonalize in a sense these equations. So that's looking for normal modes. And for this endeavor, okay, so, and what is cool about normal modes is that these are independent. And therefore describe the normal motion of the system. And to get there, we first take the continuum limit, which is sending B to 0, and then the equation of motion becomes, so what happens then, and that's why I rewrote this in this term again already. So what you can see here is if we send the distance between neighboring beats to 0, this is essentially a second order derivative, right? And the position of the beats. And so we then have gamma the R of n and t dt is equal kappa d squared R of n and t d n squared plus the noise, which obviously the noise not changing and still being a white noise, and second moment put T prime to gamma KBT delta N minus M delta T prime. Okay, now with this in mind, we now aim for a linear transformation with XP such that we have to determine this phi p such that the equation of motion becomes linear in, so we want the XDP, the XP dt, and that should then be, sorry, that's a new spring constant, which is now acting linearly directly on XP plus a new noise term. So this would be a linear formulation, which we can then, from which we can determine the dynamics of the normal modes. And so if this is our goal, what we know from the definition of XP from the left-hand side, if we just put this in here and take the time derivative, we see that this is equivalent to, there's gamma, the n phi p does not depend on time, so we only have dr and t dt. And this value we know from, sorry, there's a gamma p. And we know the dynamics of the RDT. These are specified by our overdamped equations of motions for the overdamped system up here. And so that's how we get then gamma p over gamma dn. And let me plug this in. So we now have k d squared r n t dn squared plus psi n t, and now phi p n. Now what we can do with this term is to do with this term integration by parts. So we see here that we have a second order derivative in n, and so if we do integration by parts twice, we move both integrations, both differentiations in terms of n to our normal modes phi. So integration by parts. Just as a reference, this is the formula that we have, right? And we do this twice. And then we get, okay, let me, so from the first integral, we get k dr n phi p n at 0 and n. And then from the second, that's where the minus comes from, because the second integration by parts, we get kappa r and now d phi p dn. Again at the boundaries, and gamma p over gamma dn, and now we have kr and the derivatives moved to phi plus the noise. Yeah. Now, how to simplify? We notice that we have free boundaries. So the R, the N, N equals 0 and N, these are 0. And if we take this, then this term is equal 0. And we're left with the following statement. Namely that this, that this equation needs to be equivalent to this one, right? And so from that, just comparing this term and that, we can identify how our xip, our kp, and our xp has to be defined. So we get, let me just copy this down. And plus, sorry, there's a minus. Okay. And now on the right hand side, we have xp times kp times xp, and I'm gonna insert for xp the definition in terms of phi p. So that's then minus. Don't want this. How do we get out of this? Okay, there we go. Minus kp integral over 0 to n dn. And now, for this equation to hold, we see that we have to have this term here to be equivalent to that term, right? And this here to be equal to 0. And then we can identify this integral with this. So written out in detail, it gives us gamma p over gamma, okay, d squared phi p over n squared is equal minus kp by p, defining equation for the normal modes and the boundary conditions for the normal modes. And our new noise. And integral dn by p psi. And that's an equation that we are very used to solve, which we can solve by identifying the normal modes in terms of cosines, which also solve our boundary conditions, noting that p is 0, 1, 2, and so on, and identifying our kp now as k gamma p gamma p pi n squared. And we still have freedom to choose the gamma p, and we choose gamma p such that the p noise 0 is 2 gamma p kbt, a white noise as we had defined previously. And if you make this choice and insert this above, we get that psi p alpha t is according to this defining equation, gamma p, gamma q, n squared, gamma squared. The double integral over those modes, pi n m over n. It's pi. And the noise. The noise on it without p, sorry. Better. N0, which we know is 2 gamma kb t delta alpha beta delta nm delta t. And thank God these are normal modes plus the normalization factor. So this is n a half plus delta p0. And then this equation is solved by gamma p being 2n gamma for p equal 1, 2. And the exceptional case is p equals 0, where we're integrating a 1 here. And then we have gamma 0 equal n gamma. So taken together, we found the independent normal modes. Given by, and we should stay here for free ends. If you do, like if you clamp the polymer because you're doing a pulling experiment, you have to consider different boundary conditions. And then we have 1 over n, 0 n, p pi n, capital N, r, n, t, with just copying down the spring constant of the normalized modes. Okay, sorry. And also this gamma p being 2 minus delta p naught gamma n. And now, okay, so now we have the normal modes, which we are happy with because from the normal modes, we can determine the dynamics of the polymers. So like what are eventually the modes of my end-to-end distance vector, right? So at what time scale does this relax? And for this, we first of all, again, need mode correlations of these modes. And these mode correlations in these normal modes are now, and that's why we went into normal modes, they are solved by an exponential decay, whereas the decay timescale is given by the ratio of the spring constant, of the viscosity over the spring constant. So that's the advantage of now being in this normal mode picture, where we know that modes are orthogonal to each other and decay with a time scale that's given by gamma p over kp. And we need to state the extra case p equals 0, where things are tad different. And here, let's consider the second. Sorry. Because the gamma naught is a different one. And okay, so now with these easily decaying mode correlations, we have insight into the internal dynamics of looking at the end-to-end distance vector. And to this end, we express the real space positions in terms, of normal, actually they're called Rouse modes, after the person who wrote this down first. So we can now express the position of each real space position as x naught plus 2 and summing over this all the modes of all the position and these normal modes and there we go. And revisit the center of mass, for example, dynamics. That would be integrating over all these positions. And we see if we integrate over all of them, this becomes x naught. So this represents the center of mass. This the zero's normal mode represents the center of mass. And therefore, that's why we wrote down this explicitly for the case P equals 0, because that's exactly then driving the dynamics of the center of mass, where we expect to recover the diffusion that we found directly. And indeed, if we now consider the center of mass dynamics over time squared, this is then looking at x0, sorry, minus the correlation of them, and then this correlation is 6 kBt, sorry, 6 kBt over n gamma t. So we have this diffusion of the center of mass that is given by 6 kBt n gamma as previously. So that's just a sanity check. We wanted to learn about the internal modes of the system, and that we didn't have access before going to the normal space and normal modes. So the end-to-end distance vector is here again insightful, because it can tell us about the timescales at which the polymer is internally reorganizing. And then this is our nt minus r naught t, which we can also write as the sum over all modes in between, with p being odd to keep the distance, the endpoints fixed. And then looking at the correlations of the end-to-end distance vector, sorry, there was a 4 from the 2. We get a 16 summing over all odd nodes xp t xp 0. And since these correlations are decaying exponentially, we find inserting this here. Kp, this exponential decay, where remember we had Kp being this longer expression, pi squared Kpt, and b squared scaling with p squared, and tau p was 2 gamma n gamma p over Kp. And so if we insert this, we see that we get 8 n p squared pi squared and 1 over p squared, and sorry, long expression gamma n squared p squared over 3 pi squared kbt. So what is now insightful to see is the dependence on p, and so we see that the higher p, the smaller the contribution of the mode, and so the mode that contributes most is the mode at p equal 1, right? So dynamics are governed by the longest mode, p equal 1. And so that means that the time scale at which my modes decay are the ones if I insert here p equal 1. So the relaxation time scale is gamma n squared b squared over 3 pi squared kbt, and that's the relaxation time scale. So writing down these dynamics for the individual beads of a polymer, we learned about the motion of the center of mass, which is diffusing with where the diffusivity scales with 1 over n, it's a prediction, and the internal reorganization dynamics measured by the end-to-end distance vector relax proportional to an n squared. So these are the predictions that we get from the Rouse model, which is the one that I presented you here. However, that's a short however. However, there we go. Experimentally, we measure that the diffusion of the center of mass is actually 1 over square root instead of 1 over n. And the relaxation time scale is n to the 3 over 2 instead of n squared. So typically we won't expect to get the prefactors right, but we would expect to get the scaling correctly. And so apparently we failed here. And so question is what went wrong? And so for what went wrong, we should go back to our initial equations since they are dumb. So this is where we started. We convinced us that neglecting inertia was a good thing because that's a very fast process. So that's not the culprit. So we must have neglected forces in our enumeration of the forces here. And so typically what happens is if you measure the dynamics of the polymer, you don't do this in vacuum, but there's some environment around them, which is obviously what we also take into account with the viscous forces. But the problem is that there's actually some kind of hydrodynamic interaction that we didn't take into account here. And so the extended model would be to now account for the hydrodynamic interaction. So what is missing is the hydrodynamic interaction. And just to that you heard the terms, so the better model takes them into account as the so-called SIM model, which then writes the dynamics of the modes in terms of coupling and M of via the flow fields. So here we have a flow field, and the coupling is determined by the OCM tensor. So just so that you've heard these vocabularies before, that you can place them. So there's a more extensive framework that's required to take into account to really match these equations. But we can already learn more about these also in the Rouse model, particularly because it is so simple. We can calculate a lot of properties. And so what we are mainly interested in learning about such a statistical environment as a polymer is also, regarding its dynamics, is the response, the dynamic response of a chain, and that's looping us back to, I think, lecture 2, something like, because we're gonna use the response function in the fluctuation dissipation theorem to calculate that one. So the dynamic response of the Rouse chain that's what we're after. Let me, for convenience, abbreviate. So so I'm lumping together these prefactors into an A1. Then we had 1 over p squared, and we had an E minus omega p t. Let me just note down the definitions. So this 8 was abbreviating 8, this A8 and p squared pi, and this is and note, I now switched in notations from T over TP, like a relaxation timescale, to T times omega p, which is switching to a frequency, because what we're interested in is to say, like, we take the polymer and we now probe it on different timescale. And really the way you do this, if you want to learn about the mechanical properties or the dynamics of a system, what you do is you have these devices, which we are not allowed to operate, but we have colleagues in the building that do this, where you confine a material in between 2 plates, and you oscillate with the top layer with this design frequency on this plate and you measure its response. So this is something that's readily accessible and tells you a lot about the internal structures of a system. And so now within the Rouse chain, we can make an assumption of, like, you know, if we know that a polymer is described by a flexible Gaussian chain, this is what we would expect. And so the way to what is experimentally available is the power spectrum. Which is again Fourier transform of the end-to-end distance vector tt. And so if you plug this in, what we have there is then a1 sum over all odd 1 over p squared minus infinity e to the minus I omega t e to the minus omega p t dt. And again, we know that the and then solving this integral on the right, we get 2a1 still something over p odd. And to solve this integral, we also know that the longest mode among the ones in WP, namely the p equal 1 dominates, makes this integral much easier. And then we have omega 1 omega squared plus omega 1 p squared. Yeah. So that's the power spectrum, and now we want to relate it to the response function, thinking about this shearing setting. So the power spectrum related to response function. That's related by the average here being the response and the response to the applied force. And now using the fluctuation dissipation theorem, we have, we abbreviate beta as kb over 1 over kbt. We know that the second order derivative of omega with respect to omega is given by omega beta over 2, which is exactly what we determined up here. So if you plug this in, we get a1 beta something in p odd, the 2 cancels, and we have omega 1 omega squared plus omega 1 squared p squared. Let me rearrange a little bit. A1 beta by taking out the omega 1. Then we have omega over omega 1, omega over omega 1 squared plus p squared. And so now to define the response function, given that we have this expression, we need to integrate twice over omega. So if we integrate twice, we first of all get x prime of r omega is a1 beta 1 over p squared plus omega 1 squared. And then for a second interval, That's not so fun because what we have there is to have to invoke the residues of this integral. And if we do this, we then find the response function to be A1 beta 1 over p squared minus I omega. So we see that there's a complex response function, which means that there's an elastic response to the system and a viscous response. So the complex component belongs to the dissipation that the system has. And so graphically, this means that, let me just move here. So what I'm looking at, what I'm going to plot is the inverse, because the inverse is like, has the dimensions of spring constant. And if I plot this with respect, to omega, the frequency that I'm probing it, now I have to map out both the real and the complex component. And so we see for small frequencies, and the transition here is omega 1, the longest mode. The real component behaves like a regular spring. And the imaginary part, sorry, it's meant to be a straight line. I'll try again. Here we go. The viscous dissipation is proportional to omega. And up here, it's proportional to so we see for small omega, smaller than omega 1, the response function reaches a plateau, which is the regular spring behavior. But for large frequencies, the dynamics of the polymer dominated by the longest modes come into play. The response function is proportional to I omega over omega 1. So we find a frequency-dependent modulus. So what is dominating? These dynamics are dominated by the longest wavelengths, mode, i.e. the stiffer modes. And so we really learn now that from having a polymer compared to like ideal elastic solid, we observe different response behavior in a dynamic setting due to the longest modes that are driving the system. And then so obviously this is confining us to the Gaussian chain, which is the simplest model that we can write down. But we learned that the semiflexible polymer is the more accurate description, at least of the polymers that we care about, that are making up our cells. And so I will spend the last 10 minutes, let's see, to talk a little bit about their dynamics. dynamics of semi-flexible polymer chains. And here again, the way of how we can nicely describe semi-flexible polymer chains was the weakly bending rod approximation. So really a fundamental approximation that allows us to determine important quantities. So we consider the weakly bending rod Hamiltonian. So weakly bending as a function of U now denoting the undulations. These are perpendicular. And here I'm actually, for the brevity, considering a 2D polymer. So we only consider like one transversal mode instead of two that we would have in 3D. And then integrating over these undulations squared. And also we now have x equal s. The first ansatz is to say, like, so now I have a semi-flexible polymer and bending costs energy, right? So what is that means that I have an effective restoring force if I bend the polymer that will drive it back to this rigid rod configuration. And just looking in the context of this weakly bending rod, I'm asking what is actually the restoring force that's driving the system back from an undulation. And so so we're interested in the polymer but it could be school and someone. So polymer restoring force per unit length. And then we're interested in the force for a small deviation from the rigid rod. So that would be small variation in the weakly bending rod Hamiltonian with respect to such an undulation. So considering the force per unit length, the energy variation would be to copying down the Hamiltonian, for a small variation in the undulations, dx. So that says du dx squared plus d delta, the undulation, dx squared minus the reference Hamiltonian without this variation. And so this is a quadratic term. Oh, sorry, oops, there's a square missing. So this is a quadratic term, and these undulations are small. So the quadratic term here we can neglect. So what is actually governing the variation in the Hamiltonian is the cross term originating from this factor. And that has a prefactor of 2, so the 2 cancels, 0L dx, and that's now d squared u dx squared d squared delta u dx squared, and higher orders in delta u. We're interested in the dependence on the undulations. So we do, again, two integration per parts to move the derivatives to the undulations, and then have a linear response dependence on the delta u to identify this restoring force. And so performing the integration by parts, and noticing that the undulations should be 0 at the ends, and also the derivative of these variations of the undulations at the ends are 0. So the both integration, both integration by parts terms evaluating at 0 and L drop out. And we're left with kappa 0 L dx quadratic derivative acting on the undulations delta u. And so from here, we can now then determine the bending restoring force by, given that we now have this linear relationship. So we know that delta H, delta U is then minus K d squared U, oops, sorry, 4. And so now we have a force. So now we can write down our equation of motion for in terms of the undulations. So the bending force is then balanced by a direct force, which yields the equation of motion. And again, we neglect inertia because these dynamics would relax quickly. So this is then minus K, oh, sorry, D4 dx4 plus a random noise. And where now here the stamping is, we take as 4 pi eta, eta being the fluid's viscosity of the surrounding material. And again, for the noise, we assume white noise, which means that psi x and t is equal to 0, and x t x prime t prime 2 kbt gamma delta x minus x prime delta t minus t prime. Note that here we're already in a normal mode decomposition, which warrants from the weakly bending rod approximation. So we already basically moved ourselves to the normal mode setting. And so we can look at the average dynamics of these equations. Given that the average of the noise is 0, we see that averaging, we get gamma d u dt minus kappa which we can solve by Fourier transform to identify that the uq dt is minus k minus iq to the power of 4 uq. And now this equation is linear, and so we can solve it with an exponential. UQ of T is UQ of 0 e to the minus omega QT. And here omega, oops, not P, Q. It's kappa Q to the 4. That's a very high, strong Q dependence. And so this now governs our relaxation dynamics, this factor there. And as a prerequisite for next week, I'm just going to note down the autocorrelation next week, next Friday. Namely UQT, UQ0 is then given by, here's where the noise factors in as 2 kBT over kappa L Q4. I'm going to explain this shortly. So this is the correlation of UQ0 squared, which follows again from the equipartition theorem. Sorry, follows from K over half. And so if you look at the Hamiltonian, this scales with length, and this is Q squared. Length Q squared from the derivative, and then UQ squared, and that needs to be a half kBT. And if we rearrange for the U squared, we get this prefactor. And rearranging by noticing the definition of the bending energy, we get a shorter version of LPL Q to the 4. Sorry, that was a 4 too. E to the minus omega PT delta Q prime. And that's now the prerequisite to also look at the end-to-end distance vector of the semiflexible polymer and the response function, which we're going to do on Friday. And then on Friday, we're also going to start with looking into polymer melts. And this will allow us to then look at the dynamics of droplet formation next Tuesday, which is finalizing like the content of this class, because next Friday, which is the last class, I will try to give a recap of the recaps of like what you should have learned during the class, and would be available also for asking questions, for answering questions. And just to highlight, so really droplet formation is a very eminent topic of current research falling under the framework of liquid-liquid phase separation, because it turns out that how our cells is compartmentalized in organelles is actually just a phase transition from liquid into a globular phase, which, as I said, I bet there's going to be a Nobel Prize eventually. So just wait and hang out. Okay, thanks for today.